Assalamualaikum warahmatullahi wabarakatuh. So today we're going to start our tutorial with synchronous machines. Okay, so as we know from the lecture notes and from the video presentation, that the synchronous generators are very much well spread around the world, and it's used for many applications. And therefore we will take a look at one of the example. Okay, so this is actually come out in midterm last year, no, actually this year, but this academic year, but this is actually come out last year, 2019, in the midterm. Okay, so this question is about a water turbine generator. Okay, so it is rated as 200 MVA, 12 kilovolt, 0.85 power factor lagging, 50 Hertz. It has 20 pole. It is Y connected to the mains and has per unit synchronous reactance of 0.9 and per unit armature resistance of 0.1. Okay, so you have seen previously that this per unit usage is actually basically computed, okay, if you have a base unit. So we will always have to find like a base unit for resistance and for impedance, and base unit for currents, base unit for power, for you to eventually get the real value. But it's easier in terms of per unit if you are working in the industry, because it kind of gives you the reference or the easier multiplication of the ratings, okay, when you look at the machine. So the generator actually is operating parallel with a large power system, so it's basically will be powering a large power system, so it will follow that kind of frequency lah. Okay, so let's take a look at the first question. It's 2 marks. What is the speed of rotation of the generator shaft? So this refers to the synchronous frequency, okay, or synchronous speed. Okay, so the synchronous speed, oh my god, it's green, I have to change a bit. Okay, so synchronous speed is basically 120 times the frequency of the system divided by the number of the poles. Okay, so it's 120 times 50 Hertz over 20 pole. So this will give you 300 RPM. Okay, so these generators will move at 300 RPM. So if you put the equation and the answer, you'll get 2 marks. All right. The second one is, what is the magnitude of the internal generated voltage EA? Okay, because this is a generator, of course you want to know the generated voltage at rated conditions. Okay, now we know that at rated conditions, okay, the phase voltage is actually 1 at 0 degrees, obviously, and the per unit phase current at rated conditions is IA. Okay, IA here is 1, okay, and minus 37.79 degrees. Why? Because this is 0.85 PF lagging. Okay, so because it's lagging, that's why we have this minus there, and this is cosine, cosine 0.85, then we get 31.79 degrees. Okay, so of course the power factor is basically the measurement between or the angle between the voltage and currents inside the system. So if it is 0.85, so now the current is lagging by minus 31.79 degrees. Alright, so if we want to look at the internal generated voltage, what we can do is we can do two different things. It's either we calculate everything in per unit first and then convert everything to the real values later, or you convert straight away now for phase voltages and current, and then calculate the rest of the equation with real values. Okay, so I'm going to use a PU straight away using per unit values in the equation. So we know that for synchronous machines, EA is V phase plus RAIA plus JXS IA. Okay, so obviously V phase is 1 of 0 degrees plus RA is given there per unit armature resistance is 0.1. Okay, and then IA is 1 times minus 31.79 degrees. Okay, plus JXS is synchronous reactance, so per unit as well. So if you're calculating everything per unit, you have to make sure every single term is a per unit term. Okay, then IA is 1.0 minus 31.79 degrees. Okay, so this will give you 1.63, 29.4 degrees per unit. This is not yet the answer, okay, because it wants the magnitude of the internal generated voltage. Okay, so what we need to do now is we need to find out the base. Okay, so because for per unit values, we need to find the base voltages to make sure that we can multiply. Okay, so since this is Y connected, the base phase voltage is obviously the rated, which is 12 kilovolt, divided by square root 3. Okay, so it is 6928 volts, right? So now the internal generated voltage is simply the multiplication of 1.63, 29.4 per unit times 6928 volts. So this is 11.3, 29.4 degrees kilovolt. Okay, so this is 11,300 kilovolts. All right, so if you calculate like this, obviously when you use per unit, you will get 1 marks each. Okay, the calculation will give you 1 marks. The conversion of phase voltage will give you 1 mark. And then, okay, so the equation as well, 1 mark. And then the answer is 1 mark. So this will give you 6 marks, right? For the for this part B. Okay, so you can see here that okay, there are a lot of questions. Why the per unit phase voltage at rated condition is 1, and per unit phase current is also 1. Okay, so basically when we do a calculation for each of the circuit, okay, for each of the circuit representation for the synchronous generators, okay, for 3 phase, you obviously have to do it for one single phase and then multiply for all of them. Okay, so if we look at that, so basically we're looking at V phase and IA in that circuit. Okay, so V phase is basically some values, okay, according to a rated condition, and the current is also some values. Okay, but that values is basically the same value with V phase. Okay, so this V phase is actually the value that we are basing our value, we are basing our per unit calculation on. That's why it basically divides by itself. Okay, so that's why you get 1. The same thing happens with current. So if you are computing in one single phase circuit, you will always have this value. V is 1 and IA is also 1. Okay, the degree of lagging or leading between them will depend on the phase, on the power factor. Okay, all right. So sometimes when you are given absolute impedance, for example, it is also important that if you can convert it to per unit first, it's easier because there's a lot of values that you don't know at this point. So you can in per phase circuit, you can actually calculate that the V phase and IA is also always 1. Okay, 1 here because it is divided by itself, and then just focus on the power factor to compute how much the current is lagging or leading. Okay, now because we already calculated the internal generated voltage, the third part is what are the values of generator synchronous reactance and armature resistance in ohms. Okay, alright, so in ohms, so basically now he wants the absolute value lah. Okay, so absolute value is always per unit times some base. Okay, so if per unit is current, then we have to multiply with base current. If per unit is voltage, and we have to find the base voltage. If per unit is, for example, synchronous reactance, okay, per pu, or armature resistance pu, we always have to multiply with base impedance. Okay, so base impedance is actually 3 times V phase base impedance divided by S base, okay, square, right? So here V base is, we just calculated just now, which is 6928 squared divided by S base, which is 200 MVA, right? So this is 200 million. Okay, so this will give you 0.72 ohms. Okay, so this simply is XS is XS PU times 0.72. So XS PU is 0.9. So times 0.72 is 0.648 ohms. Okay, and RA is RA PU times 0.72 ohm. Not divided. Okay, so RA is 0.1. 2 times 0.72 will give you 0.072 ohms. So this is the armature resistance and synchronous reactance in ohm. Okay, now part D. The question is, if the field current is held constant, what is the maximum power possible out of this generator? Now, if we remember in the previous lecture, in the earliest lecture on the principle of AC machines, I told you about a torque angle. Okay, this is the angle between the magnetic field of the rotor and the net magnetic field. Okay, so this torque angle is basically maximum when it is perpendicular with each other. Okay, so when the torque is perpendicular with each other, it will give you the maximum value. Okay, so if the field current is held constant, all right, and we try to ignore the armature resistance, the power is actually 3 V phase EA divided by XS times sine delta. This is the torque angle. Okay, so for maximum power is when delta is 90 degrees lah. Okay, so maximum power is when 3 V phase EA divided by XS. Okay, because this is sine 90, so this is actually goes to 1. So we get 36928 11.3 kilovolts divided by 0.648 ohm. And this will give you 362 megawatt. Okay, so now when the field current is held constant, so we are trying to maintain the amount of flux inside the machine. Okay, so now the maximum power coming from this generator is coming from the phasor diagram lah. If we remember the phasor diagram, so the power, okay, coming from out of this generator is basically simply the V phase times EA, and it is 3 times because for each of the phase, and divided by the synchronous reactance. Okay, so we typically ignore the armature resistance because it's very, very small, and that will not affect that much of this computation. Okay, so the maximum power that we can obtain is when the torque angle between the rotor and the net magnetic field is 90 degrees or perpendicular. Okay, so that will give you the maximum power. Okay, so 3 marks is basically simply if you put the equation in and then computation of this and the answer. Okay, so this is how we solve this equation. So for any per unit computation, it is important for you to use different you can use different approach, or you can use straight away PU, or you can convert it first, depends on what information is available. Okay,